World-Class Interpretation on Windows. This movie aims to present CIDR's 2011 Paradigms Interpretation Solution. We are going to run through a few slides to introduce the concepts of CIDRs, and then we are going to run the software on a New Zealand offshore dataset. Paradigm had thought CIDR's 2011 to fit any industry problem in any kind of asset. One of CIDR's foundation is to be able to handle several surveys inside a project. The data inside this project can be accessed in a single user mode or in a multi-user mode. In that case, all the users will be able to work using the same data and have a full control on the data they create inside the project. The features embedded in CIDRs make it a perfect fit for any kind of context, from prospect scale to regional scale, from exploration to development. Paradigm 2011 is also bringing visualization tools, workflows to a new level of performance. Three key points have brought us to this level of distinction. First, we need all the functionalities in any context. Then, we want to perform day-to-day tasks faster and simply accurately. We want to eliminate the doubts at the maximum to limit interpretation risks. CIDR's 2011 is released on Linux and on Windows. It allows mixed environments, freeing the users from IT constraints. For example, the IT group will be able to handle all the systems and the data in a Linux system, while all the geoscientists will be able to work on a Windows workstation. CIDR's 2011 release on Linux and Windows makes seamless communication with third-party solutions that may only be available on one platform. All workflows are available on Linux and Windows. The users will be able to use any kind of data from wells to pre-stack data. All the rest of the movie is going to focus on the software presentation on an offshore New Zealand dataset. The project we are using for this demonstration is composed by several 2D lines, several 3D surveys. We are working in a multi-survey context. The prospect area is 1,710 square kilometers with 23.5 million of traces. The full volume of amplitude is 69 gigabytes and the full project weighs 4.5 terabytes. Let's start with our 3D viewer. We are able to display many kinds of data, such as, for example, cultural data and the lease blocks that we can see there, and the New Zealand shoreline. We can visualize geolocalized picture, for example, draped on a surface. We can load several full pics and different 3D blocks. We can see that here we have a velocity volume and seismic amplitude. We are working in a multi-survey context, and we can see that we have a 3D acquisition, but also some 2D lines coming from a 2D survey. We have two wells loaded, and along one well path, we can see that we have extracted pre-stack data to QC seismic anomalies that we have encountered at the well, and QC that with the logs that we can display in our 3D viewer. A lot of keyboard shortcuts are available in CIDR's 2011. For example, pressing the Z key is hiding the object you have the mouse on. One by one, we are going to hide all the objects we have in the viewer. The seismic amplitude, the well, the pre-stack data, and we are going to keep the 2D seismic acquisition with the last well. We are going to perform seismic to well tie on a 2D line. We are now displaying the section on which we want to calibrate the well. We can compute the synthetics using default parameters, or we can open the synthetic module to specify the parameters we want to use. The synthetic module window is organized in tabs. We can work in three different modes: zero offset, non-zero offset, or use an existing synthetic. The well we are calibrating is highlighted in blue, and the three logs needed for zero offset synthetic generation, p-wave, density, and time depth relationship are selected using the active logs in the well database. The activated logs are the ones that have been validated. We now move to the wavelet and calibration tab. We can see that the well we are going to calibrate is highlighted in blue, We can see the type of wavelet we are using, the wavelet length. We can use time-varying wavelet, and we see that we have a 0.47 correlation coefficient. The correlation coefficient is computed between mean correlation time and max correlation time. Other quality indicators can be found on this line, like the PEP and the NMSE, to be used jointly with the correlation coefficient. We see that we are now using a bandpass wavelet. However, we may want to estimate the seismic spectrum and extract the wavelet directly from the seismic data. By selecting an area on my seismic line, I will estimate the seismic spectrum and then extract the wavelet from the seismic data using a statistical method. Filtering the wavelet using the graphical answers will modify the wavelet frequency and directly update the synthetic band visible on the 2D section. The NMSC value has decreased and the correlation coefficient is now 0.84. By shifting to max correlation, I increase the correlation coefficient to 0.86 and the NMSC value has also decreased drastically. The first way to perform the tie was to shift to the max correlation value. However, we can also perform that shift manually by dragging the synthetic band over the seismic section. We can have a closer look to the results by displaying the logs in a well log window. On the right in red is materialized the interval in which the correlation coefficient has been computed. In green we can see the reflectivities, in blue we have the seismic synthetic data. In black we can see that we have the extracted seismic data on the section. The match is really good in this part of the well. We can also save the new time-depth relationship and, for example, the wavelet. Everything has been done into memory and we choose which data we want to save. By clicking on apply, I see that the time depth and wavelet has turned into blue, which means that they are saved in the database. All the remaining red logs are still in memory. Now that our well data is calibrated to our seismic, we can start to have a look to structural interpretation. One of the biggest strengths of CISAR 2011 is to allow to perform efficient seismic interpretation inside the 3D viewer. As a first step, we are going to start with fault interpretation. Using my Pi menu, I put my section straight and start to locate one fault. The idea is to start picking on the amplitude, but we want to use some seismic attributes to help on the fault picking. For example, we can display coherency. However, picking on amplitude or coherency might induce some fault location errors. What we want to do is to be able to display both attributes at the same time. By playing on the weight of one attribute versus the other one, I will be able to give more importance to amplitude or coherency. The first step now is to create the fault. By pressing Ctrl F, I'm opening the Create New Fault window. I will be able to specify a name for the fault picking. I will be able to classify this fault, to specify a color for my fault picks, and I will have the possibility to create a comment to remember any kind of relevant information related to this fault. Now we can start picking our fault sticks. We follow the amplitude information and the coherency at the same time. Middle click is erasing the last point that we have picked. So we could follow the picking of the fault sticks. B is breaking the line, and using the arrow of the keyboard we can slice through our volume. This way we are going to slice the volume, pick several fault sticks separated with constant steps, and then use the semi-automatic fault tracker. For the purpose of this demonstration, we can pick one more fault stick. Again, we continue to follow the discontinuity indicated by the coherency and at the same time the discontinuity that we can see on the amplitude volume. We now have 3 fault sticks, each separated by 40 cross lines. We can now use our semi-automatic fault tracker to densify the fault picking. Based on our sparse manual picking, fault track is going to compute discontinuity based on the amplitude volume. by specifying several parameters, such as the snapping coefficient or the window width. We are going to say to the algorithm to fit more to our fault picking or to the discontinuity. By clicking Run, we are generating one fault seek per line. Fault track has generated one fault seek per line. All those fault seeks are manually editable, and we can continue the fault picking using amplitude and coherency by picking manually fault seeks on these slices. By pressing 9 on the keyboard, we are going to switch from crossline view to Z-slice. We can now zoom in and get closer to the fault to continue our picking in time slice. By pressing escape, I'm getting my picking tool, and I'm going to increase the weight of coherency on the time slice. We now see the fault better, and we can continue picking using the same fault on Z-slice. All those tools aim to make the structural interpretation more accurate and easier for the interpreter. We can see that the merging of attributes gives us the possibility to view different informations at the same time and ease the interpretation of faults. We can now turn off the fault we were picking for the exercise and display some fault that we have been picking before and view the result of our fault picking in crossline and in Z-slice. The result of the fault picking is simply accurate by simply using visualization tools, manual picking, and semi-automatic fault tracking. After picking our fault, the next step is to pick horizons. As Siders is working in a multi-survey environment, we are able to interpret on 2D lines and 3D blocks at the same time. Therefore, we want to be able to interpret on 2D lines in the 3D world. On this purpose, we are going to play with visualization tools and opacity rendering on the 2D lines to isolate the event we want to pick. We can see now that we are viewing through the 2D lines, and the minimum we want to pick is isolated from the rest of the seismic data. By pressing Ctrl H, we are going to create a new horizon that we will use to pick on the 2D lines, but also to pick on the 3D block. As for the fault, we can specify a class and select the color of the horizon. We can specify that we are going to pick a minimum and add some comments relevant and related to this horizon. By using the semi-automatic tracking tool, we are going to snap to the event. By pressing Ctrl middle click, we are going to track the minimum on both sides of the mouse. Doing so, we are going to pick the event on several 2D lines at the same time, continuing to work in a 3D environment. We will be able to pick lines intersecting the 3D block to then continue our picking on our 3D volume. We have now positioned our 3D volume close to the lines on which we have picked the event we want to follow. Using the same horizon, we are now able to track the event on the 3D block. We are performing a multi-survey interpretation. We now have the possibility to continue to manually pick our event or use the trace shape propagator. The trace shape propagator is going to track the event following a correlation criteria in a given window. We are going to threshold the correlation rate to 80%, and from the manual picks that we have been picking on the 3D block, we are going to propagate the event following this correlation criteria. To QC the result of the propagation, we can, for example, display the amplitude along this horizon in order to control how the propagator has been tracking the event we were focusing on. We can QC the horizon by displaying many kind of attributes, such as, for example, the z-value of each point of the horizon. We can also QC the result using the heredity factor. By clicking on one point on the horizon, we will be able to view the path that has been followed to generate this point. By clicking on one point of the line, we will be able to erase all the descendants of this point on the horizon. It will allow us to control the picking, taking into account the correlation coefficient used by the propagator. We can now have a look to an example of structural interpretation performed inside Earth 2011. We have displayed several horizon pickings, with the z-values, for example, displayed on the seabed. We can restrict the view and see the intersection with the on-line and cross-line. By using my Pi menu, I can use the manipulator to slice and check the full intersection with seismic and the horizons. This result will be directly sent to SCUA to create my sealed structural model. We now have the elements to create our structural framework. We can have a look to the stratigraphic features visible in this dataset. We started stratigraphic feature analysis in our 3D viewer. We are viewing the seismic data as a z-slice, and we are combining two different attributes. First, the coherency attribute is displayed in white to black, and the curvature attribute is displayed in red to blue. We see that we have some nice channelized features appearing on the slice using this combination of attributes, and the faults are enhanced using this combination. If we have a look to a deeper slice, we will see that we have also some nice channel features cut by faults, which could constitute potential trap for hydrocarbons. This portion of channel might be an area of interest. It would need more analysis to qualify it as a potential reservoir or not. We can then get a closer look by switching to a map view. We are now displaying the coherency attribute along a surface peaked close to the channelized features. We see that the faults are clearly identified on this attribute, but also that the coherency helps us to identify the channel limits. If we display the RMS amplitude, we see that the channel infilling has a totally different behavior than the surrounding area. By merging the RMS amplitude and the coherency, we can see appearing between the two faults another channelized feature. This map view gives us a lot of information about this stratigraphic layer. The other possibility is to view all those channelized features in 3D, playing with the opacity rendering on the 3D volume. We are displaying amplitude value and playing with the opacity curve. We can increase the quality of the graphics by using the brand new GPU rendering. Using the GPU is bringing many other advantages than only increasing the quality of the graphics. It allows us now to compute instantaneously attributes such as the envelope. In one click, the attribute is computed instead of taking minutes or hours of computation time. By loading opacity parameters and another color palette, we can visualize in 3D our channels and detect the high energy zones in the infilling of the channel body. To continue our analysis, we would have to analyze the frequency content of the channels to qualify them as potential reservoirs or shaly channels. To analyze the content of seismic anomalies, we can, for example, use a crossplot with AVO attributes to perform some reservoir characterization. We can visualize at the same time a near amplitude stack and a far amplitude stack. By dragging one panel on the other one, we are displaying the crossplot of the near amplitude versus the far amplitudes. We graphically compute a regression line on the near versus far crossplot, and we can use this regression line to color the crossplot. By drawing an ellipse, we can exclude points from the coloring, and we can display the points that are colored on the seismic section. We can see that the blue points can correspond to a class 2 AVO anomaly, when the red points could correspond to potential class 4. However, this is quite improbable in this kind of geological context. Several kinds of coloring modes are available. We could, for example, display a coloring grid if we were working with inversion results, for example. An important step now is to transform our time interpretation into the depth domain. For this purpose, we go back to our 3D viewer. We see that we have displayed some fault surfaces, one horizon on which we displayed the time value, and we have also displayed the velocity volume we are going to use for the conversion. All the time-to-depth operations are going to be performed directly from the 3D viewer. We choose to scale our interpretation data to depth. We can choose different velocity sources, horizon maps, formation table, cross-product relationship, but we are going to use a velocity volume to scale our interpretation to depth. The volume selected by default is the one I have in my viewer. The advantage of performing such a task in our 3D viewer is that we are going to be able to switch from migrated time to depth domain to cross-check the transformation we have been performing using this velocity volume. Without reloading any data, without changing window, we can switch from migrated time to depth scale interpretation. The icons on top allow us to switch from depth to migrated time. The QC of our depth scale interpretation is really important. So we can extract attributes from any of the interpretation surface displayed in a depth domain. For example, we can visualize the depth value along the horizon. To perform the final mapping of the surface, we can switch to a 2D view in order to map the fault outlines, the z-values, and the contours. The fault outlines are a byproduct of School 1 structural framework modeling, and all those automatically generated contours and fault outlines are fully editable. By using the magnifier glass, we can zoom on a particular area while keeping a global view on our horizon. We can, for example, delete some patchy contours visible in the magnifier glass. We can see that the portion of channel cut by the two faults is materialized by a yellow polygon. We can use the ruler to measure its size in any direction. The ruler is displaying many information, such as the dip, azimuth of the surface, and the length of the body measured. We now know that the portion of channel between the two faults is about 3 km long and 1 km wide. By using the volumetrics module embedded in the interpretation station, we will be able to estimate a gross rock volume based on deterministic parameters. On top of that, we can define several fluid contacts or define a top and a base of the reservoir using different grids. We can also define an ISO core value from the displayed horizon. We can change the units and save the table to an ASCII file in order to load it in Excel or any other desktop application. CyDers 2011 is expanding beyond interpretation limits. By making easier day-to-day tasks, by integrating all available data inside the interpretation station, and by making no compromise on technology. Thank you for watching this movie. If you have any question, do not hesitate to contact Paradigm.